Hello and welcome back to Mrs. Ogram's Maths. This video is taking you through the worked solutions for the D&D Resources booklet for probability concepts, which is paper 91585 from the level 3 externals. This is practice external assessment number 5 from this booklet. First of all, thank you to D&D Resources for allowing me to make these videos and use their materials in this way. I have popped a link to their web page in the video description so you can order paper copies of these. I highly recommend ordering the booklets and working through them yourself before just watching these worked solution videos. It's really helpful to go through in practice actually writing it out and putting pen to paper before you do the externals. Okay, let's take a look at question 1. We've got two machines. And we've got production is being split by the machine. So we've got 45% is done on machine A, and then machine B would be 55. And then we've got the probability of the two different machines producing defective output. So we've got two things in a row, which sets us up for a tree diagram where we are either going with machine A or machine B. So we've got 0.45 goes to A and 0.55 to B. For A, if they for them to get defective parts from A, it's 0.03. So not defective is 0.97. From B, chance of a defective one is 0.06. So not defective is 0.94. Then we want the percentage of the ones that are produced that are defective. So let's take a look at how we can get that as either machine A and defective or machine B and defective. So the probability of defective is going to be 0.45 times 0.03 for that top line, and then add on the option B of 0.55 times 0.06. Let's pop that in the calculator. And as a percentage, that's 4.65%. For part 2, we want to see if a randomly selected component was not defective, was it more likely that it came from A or B? So we need to compare those two probabilities. So the probability that it was made on machine A given that it is not defective is equal to the probability of it made on A and it's not defective over the probability that it's not defective. Okay, so if we look for A and not defective, that's 0.45 times 0.97. And we divide by the probability of it being not defective. Well, in this one up here, we worked out the probability of it being defective. So if we do 1 minus, we'll get the probability of it being not defective. So that's 0.9535. And let's work that through. We get 0.4578. Okay, now let's do the probability of machine B given that it was not defective in just the same way. So B and not defective will be 0.55 times by 0.94 over the probability of not being defective is 0.9535. Which comes to 0.5422, meaning it's more likely it came from machine B. Right, the last part of this particular scenario is that we've got 3 components chosen at random. What's the probability that all 3 were produced by machine B and not defective? So 3 things in a row, and they need to fit the condition that it was machine B and not defective. Well, we worked that out up here, the 0.55 times 0.94. So that's 0.517. Now, 3 components in a row. So component 1, 2, 3. Each of them have a chance of being not defective and made by machine B of 0.517. So 3 of those in a row are going to times together. So the probability that all 3 were made by B and are not defective is 0.517 cubed So that's 0.1382. And then the last bit of the question is include any assumptions we have made. And that is the first one is that these components probabilities are independent of each other. And we also assume that the likelihood of being made by B or D remains consistent throughout the process, that it doesn't change by taking components out when you're sampling, or anything else that would vary. Okay, for part B, we've got lots of information here that immediately makes me think we are setting up a three-way Venn diagram. So let's take a look. We've got company has a workforce of 100 employees with 3 production processes, A, B, and C. Okay, let's set up a circle for each one of those then. So let's have A, B, and C, and we'll work through the bullet points and tick them off as we go. I'm looking for one that covers as much as possible to start with. So that's this one just here. So 5 employees are certified on all 3 of those, so that can go in the middle. Then the 6 employees that are certified on both A and C is going to be where A and C overlap is this much, and that has to add up to 6. So we will have 1 in the other space just here, and we've used that bullet point. Then we've got 9 employees certified on process A and B. So that is this overlap here. A and B has to add to 9. So then the gap here is a 4. We've got 21 employees that are not certified on any of them. So we've got 21 sitting on the outside of this thing. Then we have, let's start at the top again. We've got a total of 48 employees that are certified on process A. So we need 48 minus 4, 5, and 1 is going to leave a 38 just here. Then we don't quite have enough information to go straight to answers in these 3 gaps here. So we're going to need to set up a little bit of equation solving. Let's start by calling this X. And just change the color. So let's say this is X, Y, Z for those bits. Right, X, Y, and Z are going to have to add up to a certain amount. We've got a total of 100 in our employees. So if we do 100, take off the 21 that's on the outside, 38, 1, 5, and 4 that we've already got on there, that leaves us with 31. So those ones have to come to 31. Now we can work out Y and Z using what we've got about process B. So B's circle has to add up to 20. So if we do 20, take off the 4 and the 5 that we've already got there, then those have to add to 11. So if we pop Y and Z being 11 back into the top line that we had, this means X plus 11 makes 31. So 31 minus 11 gives us that X is 20. So we can pop in 20 in here. In fact, I'll leave the working on there. Just 1 second. Let's pop this in as X equals 20. Okay, then we know what C adds up to. C adds up to 31. So now we can do 31, take off the 20, the 1, and the 5. So Y must be 5. And then finally B adds up to 20. So 20, take off the 5, and the 4. Leaves us with 6. Okay. If E is the number of employees certified on processes B and C but not A, calculate the probability that a random employee is certified on 2 processes only. Okay, so if certified on process B and C but not A, so B and C but not A is this section here, which means E is equal to 5. Then the probability that they're certified on only 2 has got to be anywhere that they are in 2 circles but not 3. So let's take another color now. Let's see if I can just get that one. Let's do, right, this one is B and C but not A. This one's A and C but not B, and this one's A and B but not C. So total of that we've got is 10 out of 100, or 0.1. For part 2, we're testing for independence. For that to be true, we're checking if the probability of A times the probability of B is equal to the probability of A and B. That's what we're testing for. Okay, so if that is true, then the things are independent. Probability of A, well, the total for A was 48. Probability of B, let's take a look at that. That's 20. And the probability of A and B, well, the total that overlaps in both A and B is 9. Okay, 48 over 100 times by 20 over 100 is equal to 12 over 125, or 0.096. That's not equal to 0.09. That was the 9/100ths, therefore not independent. Okay, question 2. We've got some information about men, women, married, divorced, whatever. Okay, so is a male or female employee of the company more likely to be divorced? So we need to compare those chances. What's the probability of being female given that they are divorced? So we're looking at the total for divorced is 28, and of that 10 are women. So 10 over 28. 0.357. The probability of being male if you're divorced is 18 out of 28. Which is clearly more. And although this wasn't required in the mark scheme, just to cover bases, I would say how much more it is. So it's 1.8 times as likely. Okay, if 3 company employees were chosen at random, calculate the probability that 2 of them have never been married. So the way this could be achieved, it could be the first one's married, never married. The second one's never married. The third one has. Or we could have not married, married. Sorry, rather than not married, it's never married, with the married one in the middle. Or we could have the married one first, getting picked first, and then never married, never married. So let's see how we can make up those probabilities. So never married, then married. We've got a total of 15 people that have never been married. So this would be 15 out of 100. Now once they've been picked, we've got one less person in there, so that's 14 out of 99. And then if we've got 98 people left, on this last one, it'll be out of 98. We have 15 people that have never been married, which means that there must have been 85 to start with that have been married at some point. Similarly, for the next one, we'll go 15 out of 100. Then it's 85 of the ones that have been married out of 99 and 14 out of 98. And the married ones starting this one is 85 out of 100, then 15 out of 99 and 14 out of 98. Those three ways, we're going to times them together, add them together. That comes to 17 over 308, or if you did it as a decimal, 0.05519. Now for part B, we need to represent this information we've got here. It could be done, I'm pretty sure it could be done as a Venn diagram or as a tree diagram. I think the easiest way to do this one is possibly a table. So we're going to take a look at that. We need to, and the reason it's not just easy to go straight into a Venn diagram is because of the high blood pressure thing having three categories. You might get tempted to put this as just high blood pressure or low blood pressure, but you'd also have normal blood pressure in there as well, which you're reminded of in this last sentence here. So let's create a table where we've got high blood pressure, normal blood pressure, low blood pressure. And then the other thing is about heartbeat. So irregular heartbeat and then regular heartbeat. And we'll need totals. Okay, so let's see if we can pop in here what we've got. Remembering we've got 100 employees in total. We've got 18% of them have high blood pressure. So that we'll have an 18 total for high blood pressure. 22 for low blood pressure. So then if we do 100 minus 22 minus 18, we'll have 60 in here. 16% have an irregular heartbeat. So this total here will be a 16, and 100 minus 16 is 84 for this one. Right, for the employees that have an irregular heartbeat, so we're looking at this column here, 1/4 have high blood pressure. So 1/4 of those 16 we have as a 4 in here. Those employees with normal blood pressure, 1/10 have an irregular heartbeat. So normal blood pressure, we're looking at this line just here. 1/10 of that total have an irregular heartbeat. So that'll be a 6 in this bit just here, which now we can fill in the gaps. So 10 to 16 leaves us with 6 there. 18 minus 4 is a 14. 60 minus 6 is 54, and 22 minus 6 is 16. And just to make sure I haven't done my mental maths wrong, I'm going to add up that column and check that it makes 84. Yes. Okay, so the probability a random employee has a regular heartbeat and low blood pressure. So regular heartbeat, low blood pressure is just here. So the probability that we're looking for is 0.16, 16 out of 100. So are the company employees who do not have normal blood pressure more likely to have an irregularity in their heartbeat? So we're looking for the probability of an irregular, let's say irregular heartbeat, given that they have normal blood pressure to begin with, and then compare it with the ones that don't have normal blood pressure. So given that they have normal blood pressure means that we are looking only at this line here. The chance of having an irregular heartbeat there is 6 out of 60. The probability of having an irregular heartbeat given that they have low blood pressure is going to be this line here. That's 6 out of 22. You can already see that's going to be higher. So 0.273. Probability of irregular heartbeat given that they have high blood pressure is this line just here. That's 4 out of 18. 0.22, again it's higher than the 0.1 for the normal blood pressure. And we'll finish off by saying how much more likely they are. So for the low blood pressure, we take that 0.2727 divided by 0.1 is 2.7 times as likely. And with high blood pressure, it's going to be 0.22 divided by 0.1, 2.2 times as likely. For part 3, we're looking at the idea of false positives and false negatives on test results. So we'll set this up as they have the disease, or sorry, disorder, have the disorder and don't have the disorder. And from there they would get a positive or a negative result on the test. Now let's look at the chances. So the presence of the blood disorder appears in 1% of the population. So the probability of having it is 0.01 and not having it is 0.99. The test for the disease indicates a positive result for the disease 97% of the time when the person has it. So they'll get a positive if they have the disorder 0.97, which means that 3% of the time they'll have the disorder, but the test doesn't pick it up. And they'll get a positive result 2% of the time when the disease actually isn't present. So if they don't have the disorder, they could get a positive result still, and the chance of that is 0.02. So negative is 0.98. Now, what's the probability that the employee actually has the blood disorder given that the test is positive? So the probability that they have the disorder given that they got a positive result is going to be the probability of they have it and it's positive divided by the probability of getting positive. Okay, so have it and positive is 0.001, sorry, 0.01 times by 0.97 for this top branch here. They have it and they got a positive. We need to divide by the ways that you could get a positive. So there's that one. And there's also don't have the disorder but got a positive, so that branch just here. So we'll add in 0.99 times 0.02. That comes to 0.3288, where so if they've got a positive result, the chance that they actually have the disorder is 0.3288. It's not a particularly good test if we're talking medically, because there's only about a third chance that you actually have the disorder when you got a positive result, so it would scare a lot of people for no reason. For question 3, we've got some information about 115 students and their preferences in taking biochem and physics, and then whether they are boys or girls. Assuming that there aren't any non-binary students in there, we'll set this up as a table. So we can do the preferences for bio, chem, physics, and then we'll have totals. And then boys, girls, and total. Okay, so 115 students altogether. 47 are girls, so let's do 115 minus 47, leaves the rest at 68. We've got 15 of the girls like biology best, so that goes just here. 47, oh, we used that already. 34 of the boys like physics best, so we've got a 34 in there. 9 out of the 35 students who like chemistry best are girls. So there's 35 total that like chemistry, 9 of them are girls. And we're going to work out the probability the randomly chosen student likes chemistry best given that they're a boy. So we need the 35 minus 9 gives us a 26 in that gap there. 47 minus 15 minus 9 gives us a 23 in this gap. 68, take off 26 and 34, leaves 8 there, makes that total 23, and this final total 57. Okay, so now let's do the probability that we've been asked for. So likes chemistry best given that they're a boy, so we're only looking at the boy line because that's the condition we're applying, and liking chemistry best is 26 out of 68. Or if you prefer decimals, it's 0.3824. Now we have a class of students investigating average number of children in a family. Let's fit this all on one page. And this graph is modeling what would happen if families continued to have children until they had a boy and then would stop as soon as they had one boy. So this tells us then how many children there would be in the family. This simulation was run with 600 trials. Okay, so from the simulation, estimate the probability the family would comprise 4 or more children. So probability of let's say X being the number of children, actually let's call it C for children, is going to be greater than or equal to 4. It's going to be the totals for each of those columns. So here we've got 30, 20. This looks to be about 8. And this one maybe a 5. And then a tiny little slither, a 2. You'd be allowed some leeway from reading off of those diagrams there. So if you'd put maybe a 1 instead of a 2, that would be fine. Similarly with the 5 and the 8, because they're not sitting exactly on a line. So 30 plus 20 plus 8 plus 5 plus 2 gives us 65, divided by the 600 trials is a decimal of 0.1083. Okay, now we're asked to work out the theoretical probability of a family having 5 children. So this would happen if they had 4 girls, then 1 boy. And I'm writing this out in full because the question says explain. So I'm not just going straight into calculations. So the probability of having girl, 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 and then boy will be, it's 50-50 each time. So each time we pick a girl as a half, and then the last one also for the boy is a half. And 2 to the power of 5 is 32, so that's 1 over 32. Now we've got an adjustment being made where what would change if they carried on children until they got at least 1 boy and also at least 1 girl. So if a family had 1 child and it was a boy, they wouldn't stop then. They would continue until they also got a girl. So getting one of each. So you can see instinctively this is going to increase the number of children being had, because they're not just looking to fulfill one criteria, they also want to get a girl as well. So we need to include some calculations to back that up though, not just write down that it's going to increase. And the clue to do that is where we've talked about average number of children per family in the question. So let's see if we can work out those averages. So in the first scenario of having children until you get a boy, let's think about how many children there would be in the family and the probability of getting them. So the probability that the number of children is equal to that. So we'd have 1 child, 2 child, 3, and so on. So if the chance of getting a boy on the first go is a half, and then you'd stop. To get 2 children, you'd have to go half for the boy, half for girl, and then half for boy to finish. So a half times a half is a quarter. Third child, it goes girl, girl, boy. So again, it's half times half times half. And you can see every time we're just timesing by another half. So 4 would be girl, 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 then boy. So that is going to be 1 over 16. In fact, the 5, I'm going to leave it on there because we worked it out, and the one above is 1 over 32, and that would carry on. So then the average number, so the expected number of children per family, will be 1 times a half plus 2 times a half squared plus 3 times a half cubed, and so on. Let's work out what that looks like it's going to head towards. Let's see where we're up to so far. So that's getting to 1.37. Add on 4 times 0.5 to the power of 4. Add on 5 times 0.5 to the power of 5. 6 times 0.5 to the power of 6. We can see we're tending towards, we're getting closer and closer to 2. To the power of 7, and each time we're adding on smaller and smaller amounts. So we know we're not going to get very big here. It's getting closer and closer to 2. So this is going approximately equal to 2. Now, if you know geometric progressions, you can actually put this into that, but that's not a required part of this question. So you can just use your calculator to see where it's going to. Second scenario, let's compare. So get 1 of each. Well, first of all, we wouldn't have a family with 1 child. They would have a minimum of 2. Okay, so to have the 2 children, you would have boy, girl, or girl, boy. So that's a half times a half. This is a half times a half. So each of those is a quarter, but then we times it by 2. So a quarter times by 2 is a half. Then to get 3 children, you'd have to go boy, boy, girl, or girl, girl, boy. So that's half times half, and double it for the other way it could happen. So a half times a half times a half is 1/8, and then double it is a quarter. Now you might be able to see where this is going now. If we do 4 children, it's boy, 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 girl, or girl, 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 boy. Let me just pop this in another colour to match it all up. Okay, so that would be a half times a half times a half times a half. and then twice for the two different ways that we could do that. So a half to the power of 4 is 1/16, and then double it is 1/8. And then we would have a 16th and 1/32. And you can see that these probabilities are actually the same. So it's the same sequence, but if we were to work out E of C on this one, we would have the number of children starts at 2 times a half plus 3 times a half squared plus 4 times a half cubed, and so on. So in this line here, these went 1, 2, 3, and this one starts at 2, 3, 4. So obviously this one must end up being bigger. In fact, let's just relabel this E of C in scenario 1 and E of C in scenario 2, like this. Then E of C1 is smaller than E of C2 because that series comparison. Let's just write it underneath. Is 1 times a half, 2 times half squared, 3 times half cubed. So we don't even need to work out what the answer comes to. You can tell by comparing these multiples, they're always one less. So back to answering our question, how would this impact on the average number of children per family? It would increase it. And there you have it. That's that paper finished off. If you found this video helpful, please interact with it. That helps other people to find it too, and I'm sure they will find it just as helpful. I also have a bunch of other stuff on my homepage if you want to check it out, find some tutorial videos and other worked solutions for this level 3 paper and practice resources. All right, see you next time. Bye-bye.